So the agenda for today is short from my lecturing point of view and long from you discussing point of view. And so it could be really, really short. So we're going to discuss f12, which you all read. So if there are questions, comments, etc., we could do that for a bit. And then there is one aspect of MDP is that, I've been sort of mentioning it off and on, but I did not do it formally, and so I'm just going to do it once by talking about the factored approaches for representing MDPs. So, I mentioned, for example, how state variables can be used for states, and then how to represent actions. I mentioned dynamic page networks. So I'm going to just show some examples of that, and also talk about how reward and value functions can be represented as ADDs, for example. And then mostly we won't talk about any specific algorithm. I will give you, we'll talk about a particular algorithm called SPOT, but mostly mention it, and then I'll give you a paper that you can read. And the main thing that SPOT algorithm would do is essentially do the Bellman updates directly in terms of the ADDs, rather than actually go from state to state. Okay, that would then complete the discussions I wanted to do on fully observable mark-rotation processes, reinforcement learning, which is based on fully observable mark-rotation processes, and approximate approaches for MDPs, which are kind of a mix between both reinforcement learning and MDPs, as we saw. And then you can ask also, we can also talk about any other questions you have on the other topic, on all the topics that we have done on MDPs. Now, I haven't quite figured out what the next topic is going to be. One idea would be to go to partial observability and start talking about POM-DPs. The other idea is to do something else for a change and then come back to POM-DPs later on. I haven't yet made up my mind. Hopefully I'll do it tomorrow. But if you have any likes and dislikes, if you want more and more MDPs, for example, partially observable MDPs, let me know. Either way, I'll tell you what the new topic is going to be starting Wednesday. So today we'll complete these whole three pieces together. And just to give you a sort of an idea, I would think this is at least about a third of what I wanted to, what I wound up doing in fall 2010. These are the fall 2010 lectures. We skipped the entire deterministic planning. We didn't do it here at all separately. We did the MDPs. We did the stochastic planning and efficient approaches for MDPs. That's the third part. And then we also did reinforcement learning. Okay. So that's about a third of, or probably more than a third of the course contents last time. We seem to be going very faster. Okay. So FFHub. You all read, right? Everybody, I looked at the ones that were posted until like this morning. So questions, comments, insights. So just to put all of us in the same place. So essentially, you're trying to figure out how to pick an action from a given state. And the way FFHub does is you're in state S, and it has a bunch of actions that you can pick. And it computes, essentially, if there is somebody who give it the Q values of those actions, then it will pick the action with the best Q value and then do it. Okay. In essence, essentially, it's trying to compute the Q value. The view that it takes is you consider a T horizon and then compute the Q value for a T horizon, finite horizon MDP. And then with respect to that, then figure out which has the highest Q value. And then even that becomes too hard to do, so instead of actually solving the finite horizon MDPs, Instead, we actually use the deterministic planning, and instead of actually, it becomes syntactically, it becomes swapping expectation and maximization, so that you, instead of taking max over all the expected values of various policies, you take expectation over the max values of various policies. Where a policy is a plan, and because if you have a deterministic scenario, you're going to find the best plan for solving the problem for that particular determinization. And to do that, they use the FF, fast forward, which is a deterministic plan, which we didn't discuss separately here, but those of you with background in 471 last year, you know that basically it's just a progression-based planning. It does progression and it uses a relaxed plan heuristic to improve performance. Okay. So basically it solves the planning problem using the, T horizon futures, where each of those futures themselves are sent to FF, and then FF finds the plan. You're taking the expectation over maximization. So you take basically average. Instead of computing expectation, you just compute the average of the values of each of these plans, and then pick the action that has the best average. Okay, that's what you're doing. And this basically is sort of the theory slide. There's much more interesting stuff in the paper, but at least this you should have understood, hopefully. Essentially, we are trying to, up front itself, we have done an approximation. We said to pick the action from here, really you should pick the action that is the best action, with respect to the Q star value, okay? Basically without any mention of the horizon. You already decided, well, we won't do, indefinite horizon. We will basically pick the horizon T. And the larger the T, the more effective your estimate is going to be, right? And so you decide this, I'm sorry, I don't know, I keep saying T, but H is what I'm using here. So H is the horizon depth that you're using. And you need to, and these, so basically you're trying to compute the Q values for each of these actions from the current state, and the Q values are with respect to your horizon. And since you know the horizon, you know from finite horizon MDPs that you will have a non-stationary policy, right? So QSAH is in terms of the reward of the state plus the expectation over the V star of the neighboring states, but the V star with respect to H minus 1, horizon, instead of H horizon, right? Now, what you're trying to do is, rather than compute this finite horizon policy directly, you're going to essentially empirically compute the value, okay? And the way they're going to do it is you are essentially going to pick the futures, and for each future you can basically, as long as you pick the futures and compute the values with respect to those futures, then that's an estimate that you're going to get for this, okay? And that's, the futures is mostly the paper. You have a H horizon future which you compute by, which you essentially decide by sampling the actions outcome at each time point in this horizon. Okay, so yours 1, 2, 3, 4. Let's say this is a 4 horizon. You're going to do 4 horizon evaluation of the determinations. So there are actions A1 to A100, let's say, in your world. Okay, let's say action A1 has multiple outcomes, right? There is with a 0.7, it does one outcome, and 0.2, it does another outcome, 0.1, it does another outcome. Okay, the question, of course, is when you actually do the action, only one of these outcomes is going to happen. But there is no reason for it to have exactly that outcome all the time. So what FF replan did is it either assumed that there were three different actions, three independent actions, one with just E1, one with just E2, one with just E3 as the outcomes. Or it just assumed there's only one action, A1 with E1, because that's the most likely outcome. Those were the two things it tried. Okay, both of them have problems. That's what we discussed last time. The all outcome determinization essentially will at least be admissible, in the sense if there is a path to the solution goal, it will find it, right? But the problem with it is that it tends to essentially be extremely optimistic. It assumes that you can actually pick different outcomes of the action at different times, whichever works out best for it. Okay, the most likely outcome is actually a much more reasonable idea, except it's inadmissible, because if in fact reaching the goal requires using some of the lower likelihood outcomes of actions, then you would think there is no way of reaching the goal. So you become more pessimistic. Okay, so what you do by doing this sampling, of course, is essentially you are getting the less likely outcomes occur less often, more likely outcomes occur more often, but everything gets sampled. If it is a non-zero probability, it is likely to get sampled. Okay, now of course that's easier said than done actually, because if it's a very low likelihood outcome, and if you have just a 3-horizon future you're looking at, you may never have sampled it. The very low likelihood outcomes actually may still not get sampled, and in fact there are papers written on improving FF. That we read the first version, but there is other paper I think in ICAPS 2010, which I'll mention some of the improvements they can do. But one of the improvements is essentially throw in the low likelihood outcomes that might occur in the as we saw. We will consider multiple futures from each of the under each of the actions, compute their FF plan value and average them. Okay, one of the things they do is one of the futures they pick would correspond to just FF all outcome determinization, which kills the theory, because it's no longer actually a determinization. If you take all outcome determinization, it's not a determinization in terms of sampling. But they throw that in because that way they will get an idea of what would happen if actually the low likelihood outcomes can be counted on. Okay, but in this paper they just talk about essentially the actual sampling. Okay, it's true that low likelihood outcomes are going to be sampled less often. That's the way it would. But it's better than just sampling, just assuming 0.7 or assuming all of them are independent, right? Okay. Now the one issue that people discussed in the paper is how do you construct these futures? Okay. One simplest idea is basically time-independent futures. Time-independent futures means up front you have 100 actions. So before you even start, you will say, okay, I will sample A1's outcome, A2's outcome, all the way to A100's outcome. And then stick to those samples for the entire horizon. Okay, that basically obviously doesn't make too much sense, because there is no reason why the action must have the same exact outcome every time you call it. Okay, but it makes life simple, because then essentially instead of picking 0.7 all the time, you are actually taking a coin which comes 0.7, not a coin actually, you are picking a random number and then based on that picking which outcome of A1 is going to be occurring, right? Okay, that basically still sticks to one particular sample of the action. The other idea would be to actually resample the action every time at each point in the horizon. So horizon, the time step 1 you sample, time step 2 again you sample, time step 3 you sample, time step 4 you sample. So the same action actually might have different outcomes at different time steps. Okay, so the actions kind of become non-stationary now. So the same action, because in some sense actions are non-stationary from the point of view of their effects. If you have a stochastic action, you do it second time, it may have a different effect anyway. What you're doing is you're acting as if the stochasticity has been sampled, and then you're acting as if it's a deterministic action. If it's a deterministic action, then it looks as if it's a non-stationary action, because depending on the time, its deterministic effect is changing. You see what I'm saying? So in particular, if you have actually 1, 2, 3, 4, then, and suppose, you know, I'm looking at A1, and it turns out that first time I'll get E1, second time I'll get E2, third time I'll again get E1, fourth time I get E3. Then really the action I'm playing with is A1, which has a conditional effect, which says if time step is 1, then it's E1. I mean, if it's 1 or 3, it's E1. If it is 2, it is E2. If it is 4, it is E3. So here is an action which has conditional effects. Okay. Now, it's not unusual to have actions which have conditional effects. It's unusual to have actions which have conditional effects where antecedent of the condition is the time when it was taken. Okay, that's basically what you wind up having if you actually take the kind of determinizations that is used in that paper is non-stationary determinizations. And then even, yes?
So the distinction between this and treating it as completely random is that in essence the agent is given foreknowledge of the result at each time step? Or the algorithm? Right?
Yeah, so the agent basically is going ahead and sampling the future for t steps and acting as if this were the way the future were to evolve, what would have been my best action? That's why hindsight optimization. Okay, if I come and tell you, that basically by sampling I'm telling you the action will behave this way in time step 1, this way in time step 2, etc. Okay, and furthermore notice that just as I sampled A1, I also sampled A2 all the way to A100. So in essence, in time step 1, I have an entire domain model from A1 to A100. And it's a very different, and there's a different version of it in time step 2 and time step 3 and time step 4. So it's kind of, from a deterministic planning point of view, the actions just keep changing based on the depth of the tree. The outcomes of the actions keep changing based on the depth of the tree. That's the, cute distinction from the point of view. And the hindsight part is that if I were to tell you this is how the future will resolve, what would you have done? So you're looking in retrospect. Okay, except, so normally we do this and we figured out what actually happened to our life, and then we can sit down now and say what should I have done in my high school? Knowing what actually happened to the world, as I have traveled. Okay, but this is like basically truly looking back into your past. Hindsight optimization is simulating the future, and then with respect to the simulated future, it is figuring out what is the best action for that one simulation. Do one more simulation, what's the best action? Do one more simulation, what's the best action? And the action that gets picked more often basically winds up being that maximally good action. Okay? So that's, informally, that's what is happening. Does anybody want to explain to me what's the distinction between common random number versus correlated versus independent futures? That was another thing that was discussed. So by the way, one other thing that I actually, starting, I guess, next week is the fall break, right? Next week or next to next week? Next to next week is the fall break, yeah. So, I think we have had some number of classes, and we did 2 classes where you read papers. This is actually the first class where you read papers and hopefully are discussing. I'm acting as if you read the paper. Okay, which may or may not be true. I kind of made it, sort of slightly true by making you post the reviews. Okay, But in grad classes, to some extent, you have to do this too, because there's only so much that can be explained. Either I can decide the level of abstraction for the idea and just stick to that, or I'll make you read the paper and then you understand some parts much more than others. You might understand some parts more than, in this case, my name is on one of the authors, so I might know more than you, hopefully, But some other paper I may not know as much as you did, if we are reading it together, in certain aspects. Okay, so you get to go deeper. But then if you don't read, then you just come and, it's just a talking head. So I would like to get some feedback as to which is working better for you. That's one of the things, whether we should do more of these kinds of discussions or not. And by actually speaking up, you will also give me feedback. Right? Anyway, so common random versus independent futures. What is the distinction? Yes, sir.
So one of them generates essentially the same random number at each time step for every action in every state. The other one generates a new random number for each action in each state at each time step.
Exactly. So now the question is, would these two be, so is common random number the same as time independent? It's still not, right? So it's like time independent, common random number, and independent futures. That's like the most independent, okay? So having decided not to just take one sample, now I'm going to take a sample for each action, and the action A1 once here, once here, once here, once here. The question is, now I have to do it for A2. I have to sample A2 again. The most reasonable thing to do is act as if A2 is being sampled again. First pick, one sample from A2 here, one sample from A2 here, one sample from A2 here. Okay, now the only difference is, notice that all actions will essentially have their outcomes, adding up to 1.0, right? And it's just this differentiate, the 1.0 into some different number of intervals. Okay, the way you will actually pick which outcome is being sampled is, so for example, this is 0.7, this is 0.9, good. 0.9, and this is 1.0. Okay, so I basically split the 1 to 0 into these particular intervals. Now I just, pick a random number between 1 and 0, and if I get a random number here, then I'm basically getting E1. If I get a random number here, then I will get E2. If I get a random number in here, then I'll get E3. That's what sampling essentially becomes in implementation, right? Okay, so all the common random numbers is saying is, the most reasonable thing to do is basically you toss the coin. This is the tossing of the coin essentially. Call the random number generator for each action separately, which is the most reasonable thing to do. Common random numbers is saying, I will only, for each horizon, I will make one random number. Okay, and then essentially use that same random number for all the actions. So if I pick the random number 0.6 for the first horizon, then A1 will have E1, and then the same random number for A2, let's say, is 0.5 E1, 0.3 E2, and 0.2 E3. Then the same 0.6 will tell me that E2 is the effect for A2. So I don't separately do the random sample. That's the only difference, okay? Clearly the most general thing to do is actually independently sample each action at each time step. And common random numbers is actually what was used in the implementation. There was a question as to why the paper actually shows that if you have picked the independent, if you have picked the common random numbers, then there can be examples where you'll do badly. Okay, and yet the actual implementation uses common random numbers. There is no real big reason for it. Okay, actually, again, one more thing I should mention is the whole hindsight optimization comes from, the anticipatory scheduling community. It's worth understanding that. Okay, so think of a following kind of problem. So, how do you decide where to put the fire engines in a town? Okay,
how do you decide where to park your cab in a town? Like if you're a cab guy, where are you going to hang around when you don't have, any fares? You would like to hang around in a place such that your anticipated amount of travel to the fare is minimized. Right? That's what you're supposed to be doing. Now, you don't know where your fares are going to come from. But you have understanding, so fares are the tasks, the jobs to be serviced. But you may have distribution over the jobs. Okay? There tend to be a lot of fares starting from the airport. You figured this out, and so most of the time, if you went to airport, you just hang around there. Whereas if they came to my home to drop me off, they don't hang around my home. In fact, if they hang around too long, I will actually call the police, right? So basically, the reason is they won't also do it because they don't expect my neighbor would suddenly want to go to the airport, right? So the decisions there are dependent on, in those kinds of problems, are dependent on essentially an expected distribution of goals, expected distribution of fares. And based on the expected distribution of fares, you're trying to figure out what would be the optimal policy for you. Where should you hang around? Okay, now this can also happen for basically, in scheduling, there are a set of jobs to be scheduled on a bunch of machines in a job shop, let's say. If you know what actually are the jobs, then you know how to schedule it. Okay, but if you know that the jobs will change, but you have some idea about the distribution of the jobs, then you can use that to figure out, what would be the optimal policy. And that's where the hindsight optimization came. And the difference between that problem and our problem is, in that problem, the scheduling decisions are all deterministic. It is the jobs, the goals that are probabilistic. In our problem, the goals are deterministic. People told us basically, given any particular domain, there is a goal, because that's a reward function. Nobody is changing there, okay? But the actions are stochastic. Okay, and in fact, the paper talks about this too. So the hindsight optimization came from the scheduling community, from the anticipatory scheduling community in particular, and but you can apply it to planning too, basically, where the determination is now on the actions rather than the goals. Okay, and in the case of the cab driver, basically, they have a distribution over where their fares might be coming from. They sample from the distribution. Okay, and then if, let's say, and then based on that, they'll compute what their optimal policy is, and they might do 15 samples, and then if they have good distribution information, then they will probably find that 7 of them, they're getting fares from the airport. So they'll realize that they must hang around near there. Okay, we're using the same idea, except now the uncertainty is endogenous, in the sense it's within the problem, not outside of the problem. Whereas in scheduling, in the anticipatory scheduling, it's outside of the problem. The techniques are basically similar. So you could do, for example, anticipatory planning with deterministic domain models. Okay, so I give you deterministic domain models, but I'll only give you a distribution over the goals that you might be expected to do. So then the goals will change as you're doing actions. So then the question would be, what would be your optimal policy? Okay, that kind of a problem also can be solved using FFR style techniques. The connection basically is, again, you're using, in the other case, you're sampling from the goal distribution. Okay, you're determining the goals there. Here you're determining the actions. The goal never changed. Yes.
Now, I noticed in the paper one of the big things that they had mentioned was the difference between the common random number and the independent futures, and how they actually, it seemed like, leaned toward the independent futures as being applicable toward these kind of planning domains, because the uncertainty is within the system. Or
yeah, exactly.
But the implementation uses
that's exactly my point.
Numbers.
Yes, that's exactly my point. So basically, the implementation. in this particular case, I can tell you what happened because I was part of the authors, right? I mean, you'll never know normally when paper gets written. Different parts of the paper got done at different times. The implementation was already done before the theory was figured out. Okay, and that's the reality, right? And it wasn't worth just going back and redoing the implementation because already the current implementation is doing quite well over the baseline, which is f12. Okay, that's the reality. There's no obvious huge rationale. Okay, but some other paper I won't know. In this case, I know because Sanguk actually implemented. He came up with the idea, implemented it, and already showed that it's working. We have to write a paper. Now we have to make some theory as to why it is working. And the theory said something slightly different. The deadline came. So that's what happened. Okay, but it's a good point. I mean, whoever noticed it. I mean, every paper is just work in progress. Especially conference papers better be works in progress. And in fact, actually, if you're writing papers, write papers that can be extended. Then people will extend it and cite your paper. And the coin of the realm is citation, right? So if you completely solved an area, then nobody is going to come to that area, and grad students are not going to write any more papers in that area, and so nobody is going to cite your paper. So leave some holes, that people can easily pick and then fix it. But no, that's not what we were trying to do in this particular case. It's just whatever. Anyway, so that's regarding that, and then. An aspect of the point about the hindsight optimization actually being a bound rather than exact is because, in a sense, what you're supposed to do is for each future figure out what's the reward you will get, and take the expectation over that for your policy, and then pick the policy that will give you the best value of that expectation. Okay, essentially this is what you always wanted to do, except now you're computing this expectation over futures. Okay, each future being a determination. Okay, now this turns out to be still too costly because you have to first pick a policy and then figure out its value in different futures. Take its expected value over multiple futures. The same policy over multiple futures. That's how it is. So you have one policy, right? And then however the world actually winds up resolving, you're still going to be actually doing that policy. So sometimes you win, sometimes you lose. You can't take the delusional view that when the world is not going my way, I'll wind up doing the right thing again. Right? So that's why you actually take expected value of a policy and take the policy that is the maximal, has the maximal expected value. But that's costly to compute, so one more approximation is for arbitrary reasons do max and expectation, swap the max and expectation, which is essentially like saying max. So if I were to tell you instead of taking expectation, I'm going to take a max here too. Okay, then that's essentially what you wind up having, and the point in this case is, of course, this is an approximation to the top one, and it's a new value function. It's an approximate value function called hindsight value function. And it's not actually connected to the optimal value function as equivalent, but it is, however, going to be, if you're thinking of value as in terms of reward, then it's going to be a huge upper bound on the value. If you think of value in terms of cost, it will be a lower bound on the cost. Okay? The reason it is an upper bound or lower bound, I mean, depending on the reward versus cost, is because, again, you act as if you can wind up using different policies in different futures. If you do it this way, then you will wind up acting as if you get to pick the policy based on the future. But you normally don't get that choice. You decide your policy and execute it, irrespective of what future you encounter. So that's the point that is made, that the real stochastic planners have to pick one policy that will behave well in expectation over all futures. The hindsight optimization gets to basically be greedy and say, I somehow get to pick the right policy for each of the futures. the best policy for each of the futures. And then if I have 15 futures, I'll find the best policy for each of the futures and find the values of those policies for those futures, take the average, that will give me an estimate of the Q value for that action. Okay? So that's basically what I just said. And then, the other interesting point is the all outcome determinization also can be seen as a value function. Actually, I misspoke here. All outcome determinization will correspond to max, whereas VHS just corresponds to max and expectation being 1. And then the all outcome determinization winds up being, in terms of cost, it tends to be even more optimistic than the hindsight optimization. Okay? Any questions, any comments? This is just my quick summary, hoping that you read the paper so I could talk about some of the details. But are there any other comments? Okay. So as I said, there are a bunch of ways this can be, FFR basically, they have the results which mostly show that, domains where in essence there are certain outcomes will lead you to very bad states, states with very high negative rewards. Okay. The FF, all outcome determinization tends to be too optimistic and thinks that nothing bad can happen to you. Whereas this guy will spend more time and pick actions that won't have a high chance of putting you into those bad states. And so it spends more time, and so it doesn't solve as many problems because it's actually, if you decide the width, which is the number of futures you will consider under each action, okay, then it's going to, if the higher the width, the better the estimate of the expected value. Okay. But it's also going to call FF the planner multiple times. And deterministic planning is not cheap. It's just cheaper than stochastic planning. It's a p-space complete problem. And for a fixed horizon, it's an NP-complete problem. Okay? And so it's going to spend a lot of time for all the calls of FF. And that's why if the problem was easy, if the problem was not going to mislead FF replan, then FF half doesn't do any better. In fact, it does worse in terms of time. Whereas if the problem can mislead FF replan, because then this guy will actually get out of the problem and get out of those traps. Okay, that's what the results basically show. And there was later work which I won't discuss here, but I can send a link out to you after the class, which essentially shows that basically it focused on completely implementation issues. How do you avoid calling FF too many times? What all can you do to reduce the number of determinizations you will consider for each action so that you will still get a reasonably effective action selection? Okay, that's what they wound up doing. And one, for example, these are some things that came in the later paper. One of them is just reuse futures. So if you solved a problem, and I'll come back to this after the factored approaches because it actually makes a lot more sense there. But if I solved a problem and the new problem is just a subset of the old problem, then I shouldn't have to solve the new problem again. You should be able to just memorize the plan and reuse it. That looks like not such a great, technically sophisticated idea, but memorization can save time. It basically, trades memory to time. And then the other one is the future generation. Rather than just pick only certain big futures randomly, truly randomly, you basically bias futures. Okay, so one way of biasing is, as I said, pick a all outcomes determinization future as one of the futures you consider. Okay, actually, those of you who remember BaseNet's stuff from 471. That's it's only for them. There is likelihood weighting approaches, where basically all sampling-based methods, their huge inefficiency is the low likelihood samples don't happen. And so you don't, even if you sample, you may not actually get the low likely outcome. So once in a while, what you have to do is you clamp yourself to the low likelihood outcome and then somehow make as good a use of the current sample as possible. That's what likelihood weighting did, if you remember. It did fractional weighting. That's the kind of idea that's being done here, although I don't think they had that much theory. They just did it as an implementation. Throw in certain types of futures, such as all outcome determinization future, into the mix, so that you will get a slightly better estimate of the QL. Okay, and then the third idea was, I don't know whether they actually implemented it or not, but I remember talking about it with them. Basically, not everybody needs to have the same number of determinations. Okay, think about the following thing. Suppose under action A1, I called 3 futures. Okay, and I computed their values. They are very close to each other. Then I might just say 3 is enough here. Whereas for action A2, I called one future, I called another future. Those two values, the FF plans, are very different. So I might spend more time figuring out extra plans for that. So you increase the width from under actions where you need more information and decrease the width under actions where you have enough information. This sort of is similar to some extent. This should remind you of the UCT approach, where you sort of do more samples under actions which haven't yet been sampled enough, and less samples under state action phase which have been sampled enough or which have already converged. Okay, so that's another way of reducing the amount of time taken to decide, which action to pick. Now, having done all this, this is just one type of approach for solving MDPs approximately. Okay, this is determinization-based approaches. Okay, and then there is UCT-based approaches. There is LRTDB-based approaches. Okay. Yes.
Can you go to the last slide?
The previous one.
Yeah.
Yeah.
So in this FFRA is FF free plan, right?
Yeah.
So does this answer?
All outcomes. I'm sorry. It's all outcomes FF3 plan.
So does this underestimates VHS or overestimates?
Again, you should be careful about this. I mean, if you think in terms of value as value, then it overestimates VHS.
Yes.
So VHS itself. So if you think of value as dollars, right, then VHS overestimates value and VFFRA overestimates VHS. If you think of value as a cost function, then it's the opposite. Okay. The problem is you have to get used to both. Okay, because you should know what you are using there. In this case, we are using value as a positive thing, because that's what the paper did.
So if it's positive, then it should overestimate. Because here all we were talking about reward.
Yes, you're right. I think actually these two are wrong.
Wrong, yes.
In doing VHS actually overestimates V star and VFFRA further overestimates VHS. So I changed my own mind between the two columns. One I was using the value-based and one cost-based. I think there's a better way to avoid this. V should always stand for, if you're writing it, just use V to stand for positive and J to stand for cost-based. Then you would not make a mistake. Okay? But that's a very good point. I think the paper is clear, essentially, that VHS is actually an overestimate on the value. Okay. So what I'm going to do next is essentially wrap up MDPs by talking with slides about something that we have talked multiple times before. So we were talking about different ways of approximations, and we looked at LRTDP style ideas, and we looked at UCT style ideas. That's here. And then a different way of improving the efficiency of MDPs in general is to do reasoning at the factored level rather than at the state level. And I mentioned this multiple times, but I just want to go through some details at least so that you have something specific in mind. So actions can be represented like, in fact, if you read FF up, it mixes both the state-based descriptions, all the theory is in terms of the state-based descriptions, and all the implementation is in terms of the factored representations. Because actions are thought of as PDL operators. That means it's a factored representation. Okay, that's normal because it's easier to do theory of convergence and bounds, etc. at the state space level. And then the implementations would die if you actually have to have actions in terms of state-by-state matrices. Okay, so till now we sort of assume when state space means state-by-state matrices. Okay, but you can actually write actions directly. You can think of states as being made up of features. Features can be state variables, which can be either continuous or discrete. We'll mostly today talk about discrete state variables, as we've mostly been talking about discrete state spaces anyway. Okay, so if you have discrete state variables, then actions can directly be modeled in terms of how they change the values of the state variables. So before the action, after the action. You take a snapshot of the variables before the action and what happens to them after the action. Okay? And then there are approaches for doing that. So for example, this is a particular domain where it's a robot which delivers coffee from room to room domain. Okay? And then here are all the English descriptions of the actions that this robot can do. Okay, and here is the CLK action. I keep forgetting about the CLK action. CLK is move clockwise action. The robot moves clockwise. Okay, so this kind of a, it's going in this cycle, going from hallway to hallway. Okay, so move clockwise means it'll take one step in that direction. And if it tries to move clockwise, and there are 10 states in this world, and this is the action. Description of the action. Okay, so you'll see that if you do this action from state S1, you'll get into state S2 with 0.8 probability, S7 with 0.2 probability, and then S10 with 0.2 probability. That doesn't make any sense. There was a mistake. They should add up to 1, right? Otherwise, there's additional probability. But I think the next one does, like 0.8 and 0.2, right? So that's your state matrix for actions. But you can actually represent this in terms of how it models, how it changes the state variables themselves. So again, go back here, we talked about location is a state variable, tidiness is a state variable, mail present and absent is a state variable, and so on. Okay, so this action essentially only seems to care about location and RHC and CR. What is RHC?
Robot has coffee.
Robot has coffee, and CR is coffee request. Okay, if the robot has coffee and there is a coffee request and it's a particular location, then if it does clockwise move, then its effect depends on these variables' values. Okay, that's what this picture is saying, and in this picture, essentially, these are, it's a base net where you're taking the propositions at time t, the state variables at time t, and these are the propositions at time t plus 1. And the action essentially tells you how it modifies the values of these variables from one step to another step. What happens to the rest of the variables? It just leaves them alone. So they just persist. Okay, now of course if you change one variable in a state, you are in a different state altogether. So that's how you actually compute the probability of different states. Given this, you can compute that other more complex distribution. It's a more extensional distribution. This is a more compact description of the action. Okay. Now the interesting thing, of course, is all factored representations would make sense if, in fact, actions tend to affect only a small set of the state variables. If you are very unlucky and live in a world where every action affects every state variable, then factored, non-factored, it doesn't make that much of a difference. But most reasonable worlds, an action typically modifies just a few of the state variables. And in that case, it's worthwhile representing it in this sort of factored form. So in this particular case, it is a dynamic Bayes network, and what that means is the values of the state variable here also depend on the values of other state variables in the previous time period. And it's also a Bayes network, which means that the distribution, which means that to specify the distribution of CR, I need to provide a CPT, the conditional probability table, at this, which is dependent on its immediate parents. In this case, the immediate parents are from the previous time point. So that's LOC, RHC, and CR. So here is my CPT. Now, CPTs themselves are extensional in this case. Okay, you basically give every possible configuration over these variables and the probability that CR will be true and probability that CR will be false. That's what you do. This can get pretty large. If you have n variables here, then there will be 2 power n rows here. Right? So, again, if you remember the Bayes network discussion from 471, you can use compact representations, parameterized distributions. Right? And that would essentially, kind of reduce the number of numbers you have to provide. So, for example, you could do noisy R distribution. So if you just somehow, in this case, noisy R doesn't make any sense. But if you were to use noisy R distribution, then you don't need 2 power 3 numbers. You only need 3 numbers. Okay. A more general idea is if you have a distribution like this, then you might represent it as a decision diagram. Noisy R just corresponds to a particularly simple kind of decision diagram. And the decision diagrams tend to find the structure that might be present in this table. Okay, so I just provide this, so start from location. If the location is what is this? This side, then you come to this, and then you get the probability of CR being true versus CR being false. Okay, so these CPTs themselves can be provided in these kinds of structured decision diagram sorts of things. Okay, in particular, actually, this kind of decision diagram are called algebraic decision diagrams, because these are decision diagrams which end with real numbers. There is another type of decision diagrams called Boolean decision diagrams, which ends with true and false. Those are the BDs. Okay. So they use, in this particular case, they use, you can use ADDs because they work very well for this kind of CPTs, representing them compactly. Okay. Now, so the other point to make is you could represent actions this way, where you think in terms of state variables in the previous level and how they are connected to the state variables in the next level. And this is called the 2TBN, 2 time slice Bayes network representation for this action. The other type is more like strips representation, where you essentially say, when you do this action, it will either have this set of effects, or this set of effects, or this set of effects. Okay, and they're like split into mutually exclusive and exhaustive sets of effects. And then you can then say this effect, this set of effects will occur in this branch, this set will occur in this branch, this set will occur. Okay, it turns out that they are equivalent. You can combine, you can convert this into this and this into that. However, essentially they have some advantages in some cases. If in fact there are many, many variables which wind up affecting many, many variables on this side, then the PDL representation, the probabilistic strips representation, will blow up. It will become much larger. But if you have this representation, then it's actually, even sampling becomes extremely easy. I was playing the game that my actions were like that. Notice I thought action has set of fx e1 with 0.7 probability, set of fx e2 with 0.2 probability, set of fx e3 with 0.1 probability. So I was acting as if they were strips actions. That's because, in fact, FF Hop used PPDDL representation, probabilistic PDDL representation. Okay. Now, actually, since I mentioned PPDDL, this is how it looks. Okay, this is the language. So any probabilistic planning competition planner can eat descriptions of actions of the following form. Wherein, of course, here is the name of the action, the state variable names, and then the effects here, for example, are saying, you know, this effect sets. That will happen if you do this. Okay? And all the probabilistic planning competition domains are represented in this language until the most recent one. Recent one actually shifted to this representation. Okay. If you are into probabilistic planning, then PPDDL, which is more like this representation, used to be the standard. But now there is a new standard called RGTDL, which is more like the 2TBN representation. And I showed you both. Okay. That's for the actions. Now, you can also represent the rewards and the value functions also as ADDs. Okay? Because the value function of a state should be some sort of a function of the state variables of that state. This is a reasonable assumption, otherwise where is the value coming from? The state is defined completely in terms of the state variables. So if it has a value, it should be some function of the state variables. Right? It's a very reasonable idea. And you could, for example, consider ADD's representation for the value function. So normally you have a big tabular representation for the states and their values. Now you give an ADD representation, which tells you if the state you are in has the state variable value equal to true, first variable is true, second variable is false, then its value is 0.7. If the second variable is true, then its value is 10. Okay, so that is sort of representing the entire value table as an ADD. Just as I represented the CPT as an ADD, I can represent the value function also as an ADD. Okay, despite the fact that, I mean, the tricky part of doing this discussion here is, has anybody here actually heard of ADDs before today? No, so that's the tricky point, right? And I don't really want to go into describing ADDs fully. That's why I'm just going to give you an idea that, you know, these kinds of representations exist. And if you're interested, I will give you a link that you can read that paper. Okay. But one other thing I do want to mention, however, is you know, factored representations. They don't all have to be just based on ADDs. You know, in this discussion, ADDs wound up being pretty reasonable representations. Another idea, which actually gets used in the reinforcement learning chapter in the textbook, for example, is they will assume that, again, they'll assume the states have features, F1 to Fi, and F1 to Fn, okay? And they'll assume that the value is a weighted linear function over the features. Okay, that's a huge assumption. In fact, when you do factoring, one of the tricky things is when you, I mean, what I'm saying, if it makes sense to you, it's great. Okay, which is that if you are looking at the state level, you make the least number of assumptions. You don't make any assumptions about the structure of the state, at the state space level. Whenever you do factoring, then the question becomes what language, what representation language are you going to use? If you wind up thinking that, you know, values are really, I mean, so if you use this kind of representation, then it better be the case that the optimal value for your problem can actually be representable closely as a sum weighted linear sum over features. That's actually a bias. What if, in fact, the optimal value is, you know, F1 square plus 2F3 by 4 f5 minus f7. That's the value function. You're not going to find, and all you will find in doing this is you will find the best line. So this is like, you can always fit lines irrespective of what your points are. Suppose this is the points. This doesn't at all look like a line, but I can fit a line. Here's a line. That's the best line. Right? And if I have a circle, I'll still find a line. That's a line. Right? That's a bias. Basically, if you pick a bias, then it will find the best line approximation to the circle. That's what it will do. If on the other hand you consider, second order polynomials, then you will actually be able to catch the, circle itself, but then that will have a larger hypothesis space. Okay, ADDs are somewhat more general, at least for discrete variables, than just linear sums. Okay, there is a form of ADDs called affine ADDs, which are more special ADDs, where actually the bottom value would be sort of a sum of the feature values that led you to that particular leaf. Okay, that sort of straddles the biases between simple linear feature based value function versus ADD based value function. Okay, now the reason I brought this up is if you were to go into the reinforcement learning chapter and start reading where we stopped reading, we actually stopped reading the reinforcement learning chapter right after basically the TD learning, temporal difference learning and Q learning. But after that, in the book, they actually still have temporal difference learning and Q learning with feature functions, and then gradient descent. Okay, well, what are they doing? They're essentially representing the states in terms of features, and value functions are assumed to be some weighted sums over features. And when we try to directly learn the value of states, they try to learn the weights, such that all states will have the correct values, or close to their correct values. Okay, they reduce the dimensionality because the number of features may be much fewer than the number of states, obviously. Probably logarithmic in the number of states. And you now only have the degrees of freedom is just the weights for the features. Previously, you had you had as many degrees of freedom as the number of states. Each state can have a completely different value, which is uncorrelated with anybody else, if required. Whereas now, not only would states have correlation because of the Bellman, because Bellman says if you are next to rich neighbors, you better be rich. You don't get to be poor. But then they have correlation because of these weight functions. You have to find weights such that you would actually satisfy those constraints. What you might wind up doing is find some approximation. That's why feature-based reinforcement learning techniques are pushed under approximate reinforcement learning techniques. Why is it approximate? Because anytime you pick a representation, essentially you are in some sense trying to approximate the value function. The more general the representation, the less the approximation. Okay. ADD is one, so you should think of ADDs and feature-based value functions as just two different ideas for factored representations for MDPs and reinforcement learning. Okay. So the last thing I was going to mention is essentially that the value function, just as you could represent CPTs as ADDs, you can represent reward and value functions also as ADDs. And then that leads to, anytime you have these kinds of representations, there was this one point I made last class, and I don't know how much that got through, which is you might use factored representations to specify the domain, but solve it at the state level. So all the probabilistic planning domains are given at PPDDL. Whether you use them at PPDDL level or whether you directly go to state space representation, they're given to you in this lifted level. You can compile it down. A better idea is you take it at this lifted level. I use the word lifting, which is again a conventional word, that instead of state spaces, now you're looking in terms of feature spaces. Okay, it's lifted. And You do the reasoning directly at the feature level. Okay, so in the case of reinforcement learning, normally the reinforcement learning algorithms try to update the value of a state based on either the temporal difference learning, for example. What you would do when you have gone to a factored representation is you are going to update the weights. Rather than the value of a single state, you update the weights. When you do that, one of the interesting things is in the specific kind of updates you did, there was a state, and from there you went this far, and then you basically found your neighbor's value, and then you're trying to push yourself a little bit towards your neighbor's value. You did that only to change this guy's value. Now, if your value is in terms of wi's, now you have to change the wi's. And when you change the wi's, not only did you change your value, you change everybody else's value, because everybody uses the same weights. Right? Because it better be that way. If you in fact wind up having a different weight-based function for each state, it's useless. It's still state-based then. Right? So you are using the same common weights, and when one guy is changing the weight, little into this direction, then everybody else is pushed to that direction too. And maybe that's not the right thing for them with respect to their neighbors. So then they'll fight back. And if the representation is not general enough, you will find some approximation that will make this guy is partially happy, this guy partially happy. That's why it's approximate reinforcement. Okay? So similarly here too, in the ADD-based representation too, I can represent value functions as ADDs, reward functions as ADDs. You can think of all of these as just as a representation thing, and first thing you do when you start using these representations is convert everything into extensional state tables, and then do your implemented MDP solver, which you already implemented, so you can use it directly. A better idea would be to directly manipulate ADDs to get new ADDs. Just as here, you manipulated weight functions to get new weight functions. Weight values to get new weight values. Okay? That is what's, is actually the recommended course, but then that would mean you need to actually reinvent Bellman update in terms of ADDs. Which turns out not to be hard at all if you know ADDs, which you don't, you told me. So basically, here it's just a bunch of pretty pictures. Okay, so there is your action pretty picture, and which has already been represented. The CPT has been represented as an ADD. There is a reward pretty picture, which also has been represented as an ADD. You combine these to basically go from you can go from the Bellman update is in terms of rewards and the actions and the current value function. Current value function is an ADD. Reward function is an ADD. The action outcomes are ADDs because they're CPTs. So there are direct ADD operations which you can do over these three ADDs to get the next ADD, which is value function previously was an ADD, and you compute a new ADD which corresponds to the next iteration's value function. That's what it is. Okay, and an algorithm called SPART, which I will send you a link to. Basically, it's again a small paper. It depends on how much you want to read into it. It does this direct ADD level update of value functions. Okay, but the thing that I want you to take from this is not so much that ADDs are the God-given thing for factored representation, but that whenever you go to factored representation, you have this kind of an issue, which is, you need to talk about how to do the Bellman update at that factored level. And if you're doing reinforcement learning, essentially how to do Bellman update based value update at the weight level rather than at the, if you're doing this linear function, then at the weight level rather than at the individual state. Okay, so what I would like to do is for this class, I want you all to write on the forum what you got. because I have zero idea as to what you got from, especially this factored representation description, so that I'll at least have some bearings as to, what points you're able to actually capture. Each of you get just write 100 words, or less. I saw heaven would be fine too. That would be just 2 words, 3 words. But I would be interested in seeing which aspects of what I just said here you understood, without actually going into details of any single representation. Fortunately, the way you can figure this out is, you have to pick one representation and actually do it yourself. Do the update in that representation. But then this is the way, then the ADD guy will have a separate session. I'm doing MDPs with ADDs. And there will be people here doing MDPs with linear weight functions. And there is one more guy who actually does MDPs with what's called, so there is another terminology called basis functions. It's a sort of a hybrid term for features. Okay. In fact, so some of you are doubly people here, right? Electrical engineering people. Maybe they dropped out. Okay. So in electrical engineering, for example, if you have a continuous signal, you talk about Fourier analysis for it. Fourier analysis basically is done in terms of the basis functions, which are sinusoids of different frequencies. Okay, and you basically write this signal as a weighted summation of sinusoids of different frequencies. And Fourier is famous because he showed that any arbitrary periodic signal can be represented without loss as an infinite Fourier series. Okay, which is infinite summation of sinusoids of different frequencies. And it's beautiful. In fact, when you first time you see it, it's not obvious at all that any random, a square wave essentially can be represented as a summation of multiple sinusoids, with weights. And then all you need to know as the representation for this signal is the weight space representation, the weights in the sinusoid space. Okay, that sort of corresponds to things like this, Wi times f. Okay, and there are people. Now the question, whenever you have this Wi times fi, the question is what sorts of features you are using. Depending on the features, if you have right kind of features, you can just do linear combination of those right kind of features and you will still be fine. Okay, the nice thing about linear combinations is, especially things like reinforcement learning, they can be, essentially the weight update rules become extremely simple. Because for linear functions, gradient will essentially just pick, if you do partial derivative over with respect to Wi over this kind of a sum, all you will do is you will get fi's value and everybody else just dies down. Okay, this is partial derivatives. And so that sort of gives you the direction in which to move the weights. And the gradient computation becomes extremely simple. Now the linear combination can be had if you know what should be the right functions. And some people say that for the kinds of features, the various states you have, we'll come up with features that will allow you to represent that states in linear combination of features. Those features can be quite complicated. Like, obviously just like the sinusoid features for the Fourier analysis. Okay. But all of these guys, these papers, when you read them, hopefully, when I go back now, I'll actually give you 3 different papers. I'll send you links to 3 different papers. I don't have any delusions that you'll read all of them. If you read, it's great. They're all basically doing the exact same thing, but for 3 different factored representations. And abstraction is important. If you don't see it, you will essentially reinvent wheels. When you're in the bubbles of the 14th section of a conference paper, it's hard to tell how it is different from somebody else's conference paper. They all look completely different. They're formatted differently. They have different words. But if you realize that they're all essentially doing value iteration over 3 different factored representations, that's great insight. Then you can you have a way of comparing the connections. Okay, so I think I will stop here. I will basically, this will end for us the discussion of state space MDPs, reinforcement learning over state space MDPs, and the idea of factored representations for MDPs, as well as reinforcement learning. But admittedly, that last part, I basically just flew through it. And I partly want to say that that's because I don't quite know which is the right representation that I should push you into. Okay, there are several representations, but the bigger point to understand is if you want to write the value updates directly in terms of the Bellman updates directly in terms of the representation. In fact, the third paper, I mean, you already saw ADD based, and there is a weight function based. A third idea that I'll send you a paper about is essentially if you use first order logic representations for the states, then you can do symbolic dynamic programming, basically symbolic Bellman updates completely in terms of regression of arbitrary logical formulas. And you should just put these three papers next to each other, they don't look at all like any, similar to each other. But they're all doing the same exact thing at the state space level. That's worth knowing. Okay, I'll stop.